everyone. We are starting the fifth session of our cognitive neuroscience course class today. Today we are going to talk about sounds, speech, and music perception. So we are going to cover the auditory processing, and it's going to be an interesting discussion. So please join us today, and I will try to cover these areas in 6 different sections today, trying to kind of discuss about these areas in 6 main domains, and we will kind of go through them one by one. I hope that you will enjoy them and keep on following these classes. Okay, so the first part would be some basic concepts of auditory processing. Let's imagine that you are in a really busy, crowded street like this, okay? And start to think about what are the sounds and voices and different things that you can hear right now in this really crowded street. Let's think that you are these 2 people. If you are a lady, like the lady here, or the guy here, what are the things that you start to kind of listen in the environment? Can you hear what these people are talking about? Can you start to be more focused and understand what are they talking about around you? Or trying to understand what are the things that others around you are whistling or talking about? Okay, you are still sitting in the street. You are not changing your position. You are just kind of looking in front of you. But you can start to kind of hear the sounds that you were not able to kind of hear a few seconds ago. You can start to kind of listen to things that are happening on your right side and your left side. Can you select different pieces of information that are happening outside? Can you be just focused to the music that is happening in front of you, a jazz group that are playing in front of you on the stage, or people who are talking on behind you? So how can you process and how can you discriminate different sounds and music and voices and every other thing that are happening around you and start to process them? Okay, this is the complexity of what we call kind of auditory processing, and how auditory processing could be happening inside the brain. That is the discussion that we are going to do together today. We discussed about a model to understand how the brain is processing different sort of information. Here we have different sensory inputs. Now what we have is an auditory sensory input. So we have auditory sensory kind of information that are going to the brain, and then we have what we call central executive functions, which is performing what we call top-down attentional process. So we have bottom-up attentional processing that are being derived by sensory inputs from the environment, and also we have top-down voluntary attention that is being controlled by your central executive control. And you try to do something that we call attentional window, trying to shift your auditory attention to different parts of the environment and try to kind of listen to the things that are happening around you and neglect other things. How that could be happening? Is there any chance that my auditory processing would be selecting the information that is going inside my brain? And I go back to the question that one of the kind of students raised before starting the class, discussing about, is there any chance that we have control on the visual input that we have from environment? And even when we have an kind of visual illusion from environment, let's say we can see those circles that are moving, or those sort of snakes that are moving in the kind of that visual illusionary stimuli. And we know that they are not really moving because this is something like a static picture, because it's just on the paper. And we know they are not moving, but we still feel they are moving. Can we control that kind of visual stimuli and change the processes. Now here we are asking about, can we have something like an attentional window that we shift the attentional window in the environment without even changing our position. So for the visual system, most of the time we can just change our eyes and change the direction of our eyes. How can we do that with the, let's say, auditory system? Do we have any sort of gaze in auditory system trying to have a attentional window, listening to the people who are talking on our left side, or trying to listen to the people who are on our right side? And is this going to be happening with top-down voluntary control of attention over the auditory input? And that's an interesting question, and we'll discuss about how or kind of when that could be happening or not. So that these are the questions that we are going to address today. And then we know that all these processes would be going to the kind of the next steps. We discussed about different levels of working memory storage, and then the actions, and then long-term memories. The other thing that it might be important for you to understand is another important term that we call echoic memory. Echoic memory is actually a very short auditory memory. There is another version of echoic memory, is called iconic memory. Iconic memory is related to the visual system, so it is a visual kind of processing, iconic memory. And for iconic memory, we just keep the visual information for something like 1 second. When you something around you in the environment, if you just close your eyes, you can still have the scene for something like 1-2 seconds. Or even if you kind of look at something and just kind of change your direction, you can still kind of in your memory go back and see the previous scene for something like 1 second. So we call that very short visual memory. It's called iconic memory. We have the same for the auditory system that we call that echoic memory, and it is usually for something like 2 to 4 seconds. So we have longer auditory memory, which is going to be still really short, but that gives us an opportunity to be able to listen to an entire sentence and then start to process that. So it seems that there is a kind of memory system that would bring the entire sentence to one single block to be able to process that. And we use that as echoic memory, which is called very short auditory memory. And there is a question whether we consider that as a part of working memory storage or not. So there are people who say that when we talk about working memory, the auditory working memory is going to be divided in 2 parts. One part is going to be the echoic memory, and the second part is going to be verbal rehearsal, which is usually subvocal verbal rehearsal. So we just repeat things several times, and we have mentioned that it could be called phonological loop as well, because you just kind of repeat things in our mind. And it's going to work for something like 10 seconds. So it could be working up to something like 10 seconds. Okay, so we call that subvocal. So sometimes people kind of name that as very short-term memory or short-term memory, this one as very short-term memory, and this one as long-term memory. So all the memories that we have here could be long-term memories, this one as short-term memory, and this one as very short-term memory. It is still really hard to kind of clearly define these distinctions between these systems and try to clearly define how these different levels of memories are happening in the hierarchy of auditory processing in the brain. But I will get back to this question in terms of what are the levels of information that could be stored for a few seconds, a couple of seconds, and then for something like several minutes that could be a sort of long-term memory. So we'll discuss about those steps in the next sections as well. But when we talk about temporal resolution of auditory processing, it's going to be important for us to know that what is the minimum duration of something that we can start to process that as a kind of distinct auditory sound in a way that's going to be meaningful. So it seems that the auditory system needs to have different levels of temporal resolution. We need to be able to process things in the order of milliseconds. We need to process things that are sometimes in order of 100 milliseconds. Or sometimes we need to record the entire something like 2 seconds of information to be processed that. So sometimes we just process things in the order of seconds. So we need to put together a stimuli for a few seconds, and then the entire stimuli could be processed. For example, when you're talking about, let's say, a question, when I'm putting specific intonations on different parts of the sentence, without having the entire sentence, you cannot perceive the meaning of the sentence, or whether the sentence is a kind of a question or it's just a fact that I'm talking about. So based on the kind of the different levels of temporal processing in the auditory system, we can have different levels of even neural processing that are happening in the auditory system. I will discuss about them. So we are right now discussing about some basic principles or basic questions that we have. We have started from the first question, whether we can control that in terms of the attentional control over the auditory process. What are the levels of auditory memories that we have been discussing about in terms of the auditory processing. Now we are discussing about what are the temporal aspects of auditory processing. And we are talking that, okay, it seems that we process stimuli in different orders or different magnitude of temporal resolution. We usually process the kind of the human speech into what we call here spectrogram, and in the spectrogram, we have time. I mean, this one obviously is time. This one is frequency. So we have items in different frequencies. Let's say we start from, let's say, 20 hertz, which is the lowest frequency, to 20,000 hertz, which is the highest frequency that we can perceive. And then from kind of in this range, from 20 to 100 hertz to 20,000 hertz, we put over the time dots of information that we have in the sound, okay? And the darker they are, they have higher amplitude. So if we have higher amplitude here or higher energy in the lower frequency in this time point, then that would get kind of darker. So that gives us something like a kind of a temporal dynamics of different frequencies and their intensity in the human voice, that we can just visualize the human voice as something like a diagram or figure that we call spectrogram. And people realize that small parts of that, things like, let's say, spelling a consonant, or just really kind of small phonemes like B, D, E, or kind of things that are in the level of syllables. So they could be longer. So we can start to process them in different chunks. Chunks could be really small, chunks could be 100 milliseconds, or chunks could be something like several seconds. And we'll discuss how this temporal resolution is being processed in the brain. The other dimension is going back to the kind of the features of the voice that we have, or the components of the voice that we are receiving from the environment. I'm sure that you know things related to, let's say, what do we mean by frequency, what do we mean by amplitude, what do we mean by phase, these kind of basic physics concepts that we have in terms of defining a simple sinusoidal, let's say, wave that could be basically what we call a pure tone. It's a really simple, the simplest type of an auditory sound that we can have. Let's go ahead and kind of discuss about the other aspects of that. When we talk about auditory sounds, we are talking about sound pressure level, because what we have in terms of the sounds are changes in the pressure level in the air. So we all know that it's about air pressure, and changes in the air pressure over time in something like a vibratory way is going to make the sounds. And we have kind of a measure is called sound pressure level, which is a physical concept. This one is a physical concept. But then we have something that is being sensed as something like a subjective sense. And the range of the things that we can perceive from in the subjective sense, the intensity starts from a range of something like, as you can see here, from, let's say, the really, really low intensity from something like 10 minus 12, in order of minus 12. And then we can have that in the range of something like between 1, the range is really, really large. Okay, so we are talking about a really wide range of intensities that we can hear inside the ear. And this really kind of large range of intensity could be processed in the auditory kind of processing. But we have the lowest one, the threshold of hearing. We usually kind of label that as 0. And then using an order of, we call it kind of decimal orders. And they are just relative orders. We just go 10 times higher every time. For each kind of step, we just go 10 times higher. So this one would go something like 100 times higher, because we are changing that to kind of basically 2 decibels. So we just change 2 in terms of the numbers, and we change that something like 100 times. And then exactly the same. This is the kind of the different intensity levels that we have. When we go to this level, something like here, when we go to 130 decibel, and 130 decibel is, as you can see here, 10 in order of 13 for the intensity of the sound. And that is really, really larger than what we can hear from the initial threshold of hearing. And then here we can start to have pain from the sound. And it is going to hurt the kind of the auditory system. And that is going to make a problem, okay? So if I give you something like another dimension to that, and I add frequency to that kind of graph that we had. This one is, as we have been discussing, is basically the sound pressure level. So this is the sound pressure level, and this one is decibel that we had, and we started to have 0 as the threshold of hearing, and then we go from here something like 100 times more, and then from here to here it would be another 100 times more. So that is how it goes up and up, and that's the reason that we call that decibel. So decibel is, that's exactly the meaning of decibel, units of going up and up, and every time we just multiply to 100 times when we go something like changing that to 20 decibel of unit here. These are basically relative units. Okay, and then the frequency. And what we have in terms of what is the vocal range. Vocal range is most of the time around here. So it starts from something like the frequency of 100 hertz to something like 10 kHz. That is usually the range that we talk. This is the range that we use, I mean, people use when you are in an orchestra. So you can see probably louder kind of sounds and then in a higher kind of frequency range. And this is the kind of the entire space that we can consider as something like auditory experience. So that is the kind of the space that we are processing in terms of, let's say, the physical feature of the sound that we are processing. But the physical feature is going to be reflected to the brain as auditory perception. We use the kind of ears on both sides. I'm not going to go to the details of how the ears are working, external ears, middle ears, internal ears, and the kind of the components of those things are not very much kind of interesting topics for things that we are discussing about today. But I need to kind of use something that we discussed about last sessions in terms of the frequency analysis. And we discussed about a really famous scientist, Joseph Fourier, who technically discovered the idea of when we have a signal, the signal could be decomposed to simple sinusoidal waves or simple sinusoidal signals. And it is true for, let's say, EEG signal. It is also true for auditory or sounds or auditory signals. So we know that every single sound that we have in the environment could be decomposed to single or simple sinusoidal waves in different amplitudes. So sound 1, this one could be decomposed to these 3 sounds. Sound 2 could be decomposed to these 3 sounds. Okay? Why this is important in terms of decomposing a sound to simple sinusoidal sounds in different frequencies? Because what we have in the auditory system is basically a system that is sensitive to intensity of the sound in different frequencies. So we have a sensory system inside the ear that is sensitive to sounds in different frequency. So what we basically have here, we have a built-in fast Fourier transform machine inside our brain, which is decomposing any sound that you are giving to this system to the intensity of a stimulation in different parts of this interesting line of sensors that we have for auditory kind of a stimuli. So sensors that we have here are recording things that are above something like 10 kHz. Sensors that we have here are recording things that are around 50 hertz. So when we give this system a really complex kind of sound, it is being decomposed to a stimulation of a small piece here and another stimulation here and another sinusoidal wave that is going to stimulate this part of the system. So we decompose that complex sound into small sinusoidal sounds that have different intensity. This one is going to have 10% of the entire intensity, this one something like 50%, this one 40% of the entire intensity, and the intensity would be reflected in the amplitude. But these are going to be small sinusoidal waves. So we decompose the auditory input to different simple sounds, and then we stimulate different parts of this system. But this system is going to be really long because we need to segregate different or tease apart different frequencies over the place. So we call that place principle, okay? And this place principle is tonotopic. What do we mean by tonotopic? Tone goes back to frequency, and topy is we just open it up, and different parts would have different tropy or different interest to different frequencies. So we just basically decompose the entire sound into different simple frequencies, and then we have that over that kind of interesting line of sensors. But this is really long, so we cannot have such a long channel in the ear. So what we do, we basically just make a spiral from this system, and that is making what we call cochlea. So what we see here in the ear as what we call cochlea is basically that spiral. So it goes 2.5 times around to make a spiral, and that is making the cochlea. And what we have in cochlea is the Fourier transform machine, which is decomposing the sound in the ear. And that is a really beautiful process. I'm not going to go to the details about that, but it might be interesting that those who have problems in terms of having having a completely formed ear as something like a congenital malformation in the process of development, there are potentials that are called cochlear implant. So we can make cochlear implant and put sensors in this system that is receiving sound from environment. This is the sensor that is going to be out of the skull, transforming that to electrical stimulation in different parts of a wire, and then they put the wire in this system in a way that, based on the composition that is this kind of main computer is doing outside the brain, stimulating different parts, different places within that line of sensors, trying to do whatever the system was supposed to do from the first step but design, but now based on another kind of device from outside. I'm not going to go to the details. There are lots of technical details about that, but there are kind of external aids and implants that people can use right now that could help the system when the system is kind of malfunctioning from the developmental problems. But the technical details about how these parts of this system are working, we have here what we call hair cells that are basically sensors that are sensing these things. We have different things we call organ corti, different kind of parts. I'm not going to do details about that. I mean, those who are interested, those who are taking something like kind of medical physiology or clinical physiology, I mean, those classes are full of these discussions. I'm not going to go to details. But the interesting part is just you should know that our ear are able to decompose sounds to different frequencies and in different intensity of frequencies. And then that information is being transferred to the brain. So what we are receiving is, okay, over the time, in different temporal windows, we discussed about temporal resolution. In different temporal windows, we are receiving frequencies in different intensities, and that is what we are receiving from the environment. And now we are going to go ahead and try to see, okay, how we can start to process that amount of information that we are receiving from the environment. I should also say that the information that we are receiving are going to 2 ears. So we receive information from 2 ears. And we start to decompose the information based on what we are receiving from 2 ears. And then we can start to even make something like a spatial map of what is happening around us. Because when we receive a sound from a source outside in the environment, if this sound source goes to other different sides of the environment, we can have sounds in different, let's say, lag with different intensities. So when we have a sound source on one side, the sound that is going here is faster, arrive earlier here, and also stronger compared to the sound that is arriving here, which is later and softer, okay? And that helps kind of the auditory system to make a spatial map. But it is still a question based on kind of the information that we have, how this system is able to make a spatial map around and navigate in the spatial map around us just based on the intensity of the stimuli and really a small lag or interval in terms of receiving the sound on the right ear or left ear. And that is going to be another really complex and interesting processes inside the brain in terms of making a spatial map based on the two kind of one source of information which is kind of going in different parts of the kind of periphery or environment. Okay, so that was the first part of the discussion, the kind of the session that we had today.